We're going to estimate population proportions. So let me start by a little backtrack here and talk about parameters and statistics and try and give you a little big picture approach, and then we'll talk about the results of our experiment just now. So do you remember the difference between the statistic and a parameter? What's the difference between those two things? Good. A statistic is a numerical calculation from a sample, where a parameter comes from a population. Now, typically speaking, we don't know what that population parameter is. So we conduct a sample and then calculate sample statistics, and then we hope that our statistics are good estimates of our population parameter. Kind of like what you did just a minute ago. I had you go out onto a website, random.org, and generate points here that were either on the ocean or in land, and you calculated 36 of them, or you obtained 36 of them, and you got an estimate of the proportion of the Earth's surface covered by water. So, cool, but what does that mean for us here? Well, what you did is you calculated a statistic, and let's remind ourselves of the notation here. What's the sample mean written as? X bar. Great. Someone else for the sample, the population parameter. What do we call, or what do we use to denote this? Mu. Let's move down to the standard deviation. Someone else now. Standard deviation, the sample standard deviation is S, and the population parameter is sigma. Well done. Now, one that I introduced the other day is our sample proportion is p hat. I believe we also called it p chapeau, right? The parameter is just p. But what we're hoping when we sample is that this is a good estimate of this. Or in the case of our population proportion, our sample proportion is a good estimate of the population proportion. So in terms of big picture, why do we conduct samples? It's often very difficult to know the exact value of the population parameter. We typically don't know what it is, so we conduct a sample and then calculate a statistic. And we hope that we get a good estimate of a population parameter. And in general, we hope that our sample statistic is a good estimate of this population parameter. That's what we're hoping when we conduct our sample. This is kind of going to guide us in a lot of what we do in chapter 7. We're going to construct confidence intervals. And the reason we're going to construct confidence intervals is because we know that when we take a sample, that we're likely to get different values. And it's unlikely that we'll exactly nail the true population proportion. So let's look at our results here. I had you guys sample. I had my morning class sample. So out of 36 tries, how many times did you end up in water? Well, it varied depending on the group. We had as high as 30 and as low as 24. And they gave us different estimates of the true proportion of land on the Earth's surface, or the true proportion of water, depending on how you want to look at it. So overall, we got about 3/4 of the Earth's surface was covered by water. That's our global, or it's our combined estimate. One thing this should show you, though, is that different estimates, different samples are going to lead to different sample estimates. So we're not exactly guaranteed that we nailed the population proportion, did we? And what is the true population proportion? Well, a lot of times you just don't know. But this time there actually is a way we can find out. It's not going to be true in general, but we can find out. Let's see. Right here. You can ask Google, right? Google knows everything. All right, you can't always do that, though. So the true population proportion of the Earth's surface covered by water would be what? 71%. All right? Well, I don't think anyone in our sample hit that, did they? But what this process is showing you is that we need to surround our best guess with a little margin for error, a little interval that says, okay, here's our best guess, but it could be off. You know, even though we think that 75% of the Earth's surface is covered by water, it could be as high as 80 or as low as 70. It just kind of depends. We need more data to process that. So we're going to surround things by a margin for error. So it's the maximum likely difference between your statistic and the true parameter. Let's see how that's going to work. And we'll start with problem number 12. So this is section 7.1. This is on page 312. So they're giving us a confidence interval for the proportion of blue M&Ms. So when you open up a bag, what percentage of them are blue? And it gives it to you like this. 0.270 plus or minus 0.073. And they want us to write it in a different form. So let me copy that down, and we'll work through it. And then we'll work another problem that works kind of the opposite direction. So problem number 12, we get 0.270 plus or minus 0.073. What is this? That 0.270 is your p hat. That's your best guess as to the true proportion of M&Ms that are blue based on your sample. The plus or minus 0.073, that's your error term. You could rewrite that in a different way. You could write that as an interval. So in terms of an interval, you could do p hat minus e is less than p is less than p hat plus e. And that interval is called your confidence interval. So what's that going to look like for this particular example? Well, it'd be 0.270 minus 0.073 is less than p is less than 0.270 plus 0.073. So we're not sure exactly where the true proportion of blue M&Ms is, but it's somewhere between 0.197 and 0.343. So about 20% and 34.3%. Somewhere in there is where we think the true proportion of blue M&Ms is. Notice that in between these two things, I've got p, not p hat. That's because p represents the true proportion of blue M&Ms. True proportion of blue M&Ms. Do I know what the true proportion is? No. No, I don't. Not unless you're M&M Mars, right? In that case, you do know the true proportion. But for us, we're just estimating it. And we think it's somewhere in this interval. We know and we saw that if you take different estimates or different samples, you're going to get a different sample estimate. That's why we have to surround our sample estimate, our point estimate, by this confidence interval. It's because we know at the deep of our, bottom of our hearts, we know that that's probably not the exact answer. Let's work with this in another direction. But before I move on from problem number 12, are we okay? The only goal of this problem was to rewrite it from this form right here to an interval form right here. So this would be your answer for problem number 12. This part right here. TJ? Well, E is something you have to calculate. And the calculation for E is a little bit involved. And I'll go over that in a minute. But for now, E is just our error. That's where we're surrounding ourselves with a little cushion because we know that's probably off a little bit. Anything else? Let's back up a step and look at problem number 10. Problem number 10 is going to ask us to reverse this process. So with problem number 10, we're going to start out with an interval like this. We're going to try and write things as p hat plus or minus e, like that. So you're going to go kind of backwards. This time we're dealing with a percentage of M&Ms that are orange. And that confidence interval for problem number 10 is 0.179 is less than p is less than 0.321. And I want to write it in the form of p hat plus or minus e. So let's see if we can't determine those things for this one. We'll start by finding p hat. P hat, that's your best guess. That's your point estimate. Saying, look, if I had to guess, it'd be this. So p hat's going to be right in the middle here. How can I find what's right in between those two? Nice. Take the average. So 0.179 plus 0.321. Add them up and divide by 2 gives me 0.25. And that's my p hat. That's what's right in the middle. Cool. But now I need to figure out, well, what's the error term? How far do I move from the middle to get to here or to get to there? There's a couple ways you can figure that out. Any guesses? What can I do to figure out that distance? The E. So you can do 0.321 minus 0.25, that'll give you E, or 0.25 minus 0.179. Either way, you can get E. I'll just do it this way. 0.321 minus 0.25 gives me 0.071. You could have done it the other way. E would be 0.25 minus 0.179. Again, it's 0.071. Either way, we've got all the information we need. We've got p hat. We've got E. So to rewrite this then, as asked, we could do 0.25 plus or minus 0.071. And that would be your final answer for problem number 10. Okay on that one? All right. Now TJ asked, well, how do you get E? And the short answer is that it's not easy. All right, it's a little bit involved. So let me go through it with you just once to help you appreciate just how good you really got it. No, it won't tell you what E is. No, it's not that simple. In fact, the book would have you do a lot of work. But let me tell you the general form of a confidence interval. So, confidence interval for a population proportion. And let me that in here. There you go. So we're going to first need to define a couple things. Well, let me write it like this. Let's go p hat plus or minus e, where e equals this lovely creature, z sub alpha over 2 times the square root of p hat times q hat over n. Let me make some more definitions. P hat is going to be x over n, where n is your sample size. And x is the number of successes. What do you suppose q hat's going to be? 1 minus p hat. Alpha is going to be our level. I should do it this way. 1 minus alpha is our level of confidence. And finally, z sub alpha over 2 is the points in the z distribution with alpha over 2 of the area in the right tail. And I think that covers everything. So, wow, there's a lot going on there. Let's see if we can't figure out a confidence interval for our data this morning. Try and figure out, well, where do we think the true proportion of Earth's surface covered by water actually lies? So, give you a chance to catch up to that, and then we'll pick up some data for ourselves. So it's p hat, q hat divided by n. Just a reminder, I post the notes on D2L, so if there's something that goes by a little too quick and you want to look back at it, you should be able to find them on D2L. Let's just take a quick peek back at our spreadsheet. So, out of our 252 tries, we had 189 points that landed in the water. So it would look like this. X is 189, N is 252. We're gonna create a 95% confidence interval. 95% and 99% are the gold standards. You typically use either one or the other. Let's see. So if we have a 95% confidence level, that's 1 minus alpha equals 0.95. That means 1 minus 0.95 is our alpha, or 0.05 is alpha. Looking backwards, we need to calculate z sub alpha over 2. That's going to be z sub 0.05 divided by 2, or z sub 0.025. That's the point from the z distribution with 2.5% of the area in the right tail. You can get this from Google Sheets, or you can get it from your graphing calculator. But let's try something new here. Let's try getting it from Statistic. It's It's going to be pretty easy from Statistic. So let me show you where to find that. So I'll open up Statistic. I'm doing it online. You can download it. You should see a menu item for analysis, and then right underneath that is an option for probability distributions. So choose that. When you click on probability distributions, one of the options given to you is the one that we want, which is the normal distribution. So I'll click that. Now you can type in one of two things. You can type in the z-value, it will give you the area, or you can say, all right, this is the area that I want. And let's look back for a second to see what area we want. I want the area that, or the point that represents 2.5% of the area in the right tail. But that's not the way Statistic works. Statistic works with the area in the left tail. So if 2.5% of the area is here, how much of the area is over here? 2.5%, not 25%. 97.5%, right, or 0.975. So let's go back to Statistic and type in 0.975. Oops. 0.975. And click Evaluate, and bam, it gives it to us. There you go. 1.96 is the z-value. Again, you can get that off of Google Sheets or off of your graphing calculator. Bottom line is 1.96. Let's calculate a couple other things here. I need p hat, which is going to be 189 over 252. Wow, that's exactly 0.75. Didn't expect it to work out quite so even. So if p hat is 0.75, what's q hat? Good, 0.25. Nice. And we're going to put those two terms together along with n and calculate our margin for error. That is the e term there. So that means calculating e equals 1.96 times the square root of p hat, which is 0.75 times 0.25, divided by 252. Okay, let's see what that looks like. So 1.96 square root of 0.75 times 0.25 divided by 252. And there we go, 0.0534. I'm just going to store that in x out of my convenience. So 0.0534. So p hat plus or minus e equals 0.75 plus or minus 0.0534. Let's turn that into an interval. P hat minus e less than p less than p hat plus e. So what would that be like as an interval? Well, let me do it this way. 0.75 minus, now I stored this value in x, so minus x and 0.75 plus x. So we're not sure exactly where the true proportion of land is, and the exact proportion of Earth's surface covered by water is, but we think it's somewhere between about 70% and 80%, somewhere in there. So 0.697 less than P is less than 0.803. Somewhere in there. That's our confidence interval. Now, it's not terribly precise, right? I mean, you got a range of like 10 from top to bottom. But, you know, it narrows it down enough. Please. Correct. Yeah, that's the data that we ourselves generated earlier this morning. So that was back here. So that was the number of successes out of the total number of trials. Yep. Marcel? So where I got the 1.96 from, I picked that out of Statistic. So, oh, okay. Yeah, there you go. Yeah, you want to put it in the area to the left. All right. Are you ready to make this a lot easier? All right. Let's make this a lot easier then. So, compare all the work we just did, which is old school, with what we're going to do new school. New school, let's go up to analysis. Then go down to confidence intervals. We're dealing with one proportion sample. So click there. Our confidence level, well, we wanted a 95% confidence level, so we're okay there. What was our sample size? 252. How many successes did we have in that 252? 189. Great. Ready? Bam. So the middle one's the one we want to use. The bottom one is similar, but I think the bottom one comes from a non-parametric approach, which we're not going to discuss till the end of the semester. But, wow. So one more time, it was analysis, confidence intervals, and then the first one there was proportion one sample. Wow. That's pretty slick. That's a lot easier than students' generations before you had to deal with. And actually, even what we did was even easier than what I did to start out with when I was starting to teach this, because we didn't have to look up the z-scores in the back of the table. All right, we just got those using technology. Used to be you'd have to look up your z-scores in addition to everything else. So, bottom line, I'm saying you guys got it pretty good. You can use statistics on an exam, but here's what I ask. We're spending less time in the number crunching, but I want you to be able to interpret this. So let's work hard on the interpretation, because ultimately you want to share these results with somebody who may not have a statistics background. You want to be able to say to somebody, here's my results, and the important thing is you explain them in English, right? I mean, if you start saying all kinds of things about, well, our point estimate and our confidence interval was this, and our margin of error, you want to say it to them in nice, simple terms. So let's do that for this one. And you should try and follow the general form of this when you're writing your answers. So this says we can be 95% confident and that's the way I want you to start out these things, is talking about the level of confidence that you use to construct this, that the true proportion and I like you describing what parameter that we have here. The true proportion of the Earth's surface covered by water is between 0.697 and 0.803. Or you could say between 69.7% and 80.3%. But that hits all the little buttons that I want from you when you're working on these types of problems for yourself. You express the level of confidence. You talk about the true proportion and then describe what that is. The true proportion of the Earth's surface covered by water. So describe it in words. And then you give your results numerically. It is between this and this. It's exactly the way I want things. Deviating from the script is a little bit dangerous. A lot of times people want to say something about a probability. Let me be very careful in saying this. This is not a probability. It has nothing to do with probability when we talk about the 95% level of confidence. What it's saying is that if we did this procedure again and again and again, say 100 times, that 95 of those times, this interval would contain my true population proportion. Now, we looked it up on Google, right? It was the true population proportion was 0.71. Is that in my interval? Yeah, it is. If I did this with, 99 more classes, 94 times out of those 100, I should end up with an interval, probably a different interval, but an interval that contained that proportion. 5 times out of 100, I won't get so lucky. But that's what that level of confidence expresses, is how often you should end up with an interval that contains your true population parameter. Whew. All right. Who wants to be the first to ask a question? Everyone's shy. How about being the second to ask a question, okay? Does that work for somebody else? No? Let's try a few more of these. And we're going to continue to work with these on Statistic. But, Statistic, I believe, just makes our life a lot easier. And we can spend time focusing on the bottom line result, which is explaining that in words. Okay, so let's move up to problem number 18. One of Gregory Mendel's famous genetics experiments yielded 580 peas with 428 of them green and 152 of them yellow. First thing first, find a 99% confidence interval estimate for the percentage of green peas. So whatever that percentage is, call it P. We don't know it. So we're going to estimate it. We're going to come up with an estimate. Let's decide what that estimate is. What's our best guess, our point estimate? What's P hat in this case? So P hat is 428 over 580. Let me move away from this a little bit and write some of these things down so you can follow. So for problem number 18, N is 580, X is 428. We want a 99% level of confidence. And there's something a little bit old school in me that says I want you to be able to find alpha. I think that's a skill that we're going to need to know. So 99% is 1 minus alpha, or alpha is 1 minus 99%. 99% as a decimal is 0.99. So alpha itself is 0.01. So we got this 99% level of confidence. That's great. Let's see if we can't find a couple things. We already set up a fraction for p hat. That was 428 divided by 580. 428 divided by 580 gives me 0.738. That's one drawback about Statistic, is that it doesn't actually give you p hat and all the output, which I'm not sure I understand, but it's not a hard calculation. Let's use this information to find a 99% confidence interval for the proportion of green peas. So I'll go back up here and do a 99% confidence interval. Sample size was 580. How many successes do we have? 428. Wow, this is just too easy. Wait a minute.
That was easy.
Yeah. All right. That's pretty nice, man. Now, our confidence interval, the output that we want to use is going to be the one here in the middle. So let's write that down. So our confidence interval is going to be between 0.691 is less than p is less than 0.785. Let's take note of something else here. Our margin of error is 0.04703. So I'll also take note of that. E is 0.04703. So that if I wanted to, I could also rewrite my expression like this. Instead of writing the confidence interval, I could write it as p hat plus or minus e would be 0.738 plus or minus 0.04703. And if you did this plus this and this minus this, you should get these two values right here. So far, so good on problem number 18 here. Yes, that's an important part. We're going to do that next. Thank you. So the interpretation of that is important. Let's remind ourselves what P is. P is the proportion of green peas from these kinds of experiments. So we'll start out with, we can be 99% confident that the true proportion of green peas is between 69.1% and 78.5%. Again, you're hitting all the right buttons. You express your level of confidence. You describe what the parameter is, and then you give the confidence interval. So those three things should be part of your statement here. Please don't use the word probability in this. Olivia, okay. Are you okay with the interpretation here? I mean, it's nice. It's something you could share with somebody who hasn't taken a stat class. They could look at it and go, okay, yeah, I understand what that's saying. So, all right, your turn for one. Is there anything else on problem number 18? Let's turn our attention to something that seems to be in the news a little bit more and more. Problem number 20. The drug OxyContin is used to treat pain, but it's dangerous because it's addictive and can be lethal. In clinical trials, 227 subjects were treated with OxyContin. 52 of them developed nausea. Yeah, I think he took the high road on this. He didn't talk about anything else I expected him to do, but he's just talking about the people who have an adverse reaction to taking it in the first place. So you develop nausea. So we want to find a 95% confidence interval for the percentage of OxyContin users who develop nausea. So you've got all the numbers you need there. Give it a shot and see what you can come up with. See if you can come up with a 95% confidence interval estimate and then interpret it in words. So if you're watching my videos and you see this little pause sticker up here, I don't have a pause button because of the way my software is configured. So this is my manual pause. And you just fast forward until you don't see the pause image anymore. It should be good. So it's my workaround. don't have a computer or a calculator, at least borrow a calculator. Has everyone got at least one? So this is our relevant information here. We've got 52 successes out of 227 trials. Successes is kind of in quotes there, right? Not really happy that people have nausea, but that's what it's called, number of successes. And we'll see that as we enter that into Statistic. So this time we want a 95% confidence level. Our sample size was 227 and 52 successes. So let's take note of a couple things. Our margin for error is 0.05, 0.047 we'll call it. So E is about 0.0547. And our confidence interval itself is 0.1744. I'll call it 0.174. Is less than P, is less than 0.284. The important thing is to interpret this in words. Assuming we can do the rest of the part correctly, that is, plug in the values, then what would be the interpretation of this in words? Does someone want to give theirs a shot? Beautiful, beautiful. Let me write it down here. We can be 95% confident that the true proportion of people who develop nausea using OxyContin is between 17.4% and 28.4%. Wonderful. Thanks, Jasmine. Are we okay with our conclusion here? This much. You getting comfortable with the format of that conclusion? You don't want to mention probabilities because there's really only one of two possible probabilities. It either contains it or it doesn't contain it. So we don't know which one. It's either a 0 or a 1 are the only probabilities that are legitimately associated with this. George? This part right here, yes. Well, I mean, I could ask you any of these things, but I mean, this is just a matter of reading it off from the output from Statistic. Now, there is another way to get this. For those of you who have a graphing calculator, you can do it with the graphing calculator as well, and it's just as convenient as it is with Statistic. So you're going to press the stat key, then the test key, and then scroll down to one population or one prop Z interval. So it's a little ways down to get to that last one, but let me start from afresh. So we'll start by pressing stat, and then over to test, and then down to one proportion Z interval. And it's just menu driven from there. We want a 95% interval. Scroll down to calculate, and it's got it for you. Oops, I guess I blew by it too fast. One proportion Z interval. There we go. I guess what I like about this is that it also gives you p hat. which is nice. It's not a big thing. The downside is that it doesn't give you E, right? If I asked you what E is, then you have to figure out what E is. But that's not too big of a deal. Here's another question for you and follow up to this. Suppose that I go back and said, you know what? I don't want to be just 95% confident. Another common level is to be 99% confident. What do you think is going to happen to the width of this interval? It makes sense that it would expand, right? Because if you want to be more confident, then you're going to give yourself more room for uncertainty. So let's see how much that changes this interval. Let me go back, at least here, stat, over to test. One prop z-test and do 0.99. And let's see what happens to the interval now. And it does get wider. It's going to go from 0.157 to 0.301, call it. So it's a couple points wider on either side. So that makes sense. It's in line with our expectations. How are we doing on section 7.1? You okay with the stuff there? All right. For homework, try problems 1 through, call it 31. Good luck on that.